Hey, so I'm a little late getting started today. Sorry about that. Um, I was making coffee and I poured so much into my cup that walking back to my office, I had to like kind of stop every few steps to make sure that the coffee didn't splash out of the mug. So it took me a few minutes to get back here, and it was too hot to drink, so I couldn't like sip it down to uh, get get some of it out of it. Um, but let's get started. Um, so last time we were working on implementing the. Let me see if I have the paper still up. I don't. So let's. Oh yeah, here it is. It's just on the wrong desktop. So here we go. So yeah, we were implementing this, which was really confusing because it didn't really make a lot of sense to me. The way that they were doing the remove visited nodes and using this here. So I played around with it for a little bit and ended up eventually with this here, which is slightly different. So I actually start with the outgoing edges of each dominator, because we already have the dominators. We don't have to figure out any of that stuff. And I start keeping track of visited edges as opposed to visited nodes. And as I go through those edges, then I add every node or target node's outgoing edges to our edges to visit. Now, if the edge has been visited, then it's gonna just kind of ignore it, I think. But I think we're guaranteed that these, because we're going through the target edge, that these edges have not been visited yet, unless it's a cycle. So then when we get down here, it's easier to figure out what we need to actually pop off, because we're looking for the edges of that node in the visited edges. And if the visited edges contains all of the edges of a particular node, that means that we've visited all of its descendants, and we can pop that one off. And so we can just sit here and loop over this until we get to the point where we don't have any more nodes that have all their descendants visited. So what that ends up getting us is something that looks kind of like this, where we have a starting block and an end block, and then these are all of the paths that can get there. And for the most part in this binary, there's not a lot of like multiple branches that will get you there. Let me bring up Binary Ninja. I think that's also on the other display. Oh, no, it's here. Cool. All right. Let's go ahead and hide this. Oh, no, it won't go away like that anymore. Get rid of you two. There we go. A little bit bigger. So like in this one, let me clear this. I think I already imported it. Oh wait, no, I've just been copy pasting it. Yeah, so if we do this and then take the nodes in the slice can kind of see here. Let's see, what's got multiple branches? Does anything have multiple branches to it? Not in this one. Let me, phase 3, I think? Is that the switch? Yeah, I don't want that one. I want phase 4, I think. Yeah, actually main is a good one. Yeah, because this one's got the this way and then this way. So let's see, we want from 0 to 24, which I believe is hex 18. So where's hex 8? Right here. Okay, so we've got this one, which is going to be 0 to 7. Oh, yeah. It's going to be the false branch to 7, and then the unconditional branch to 24. And then we've also got the true branch from 6, then the false branch to 11. Oh, hex 11, so that's 17. And then the true branch to 24. So that is cool. And then yes, I am, you are correct. So then I was kind of thinking about it after I did this, and I know that these graph slices are then used to get the reaching condition, which is like what conditions from this basic block to this basic block need to be fulfilled in order to get here. And it then occurred to me that I don't need this because I can do something like, I don't know, I am like flailing around, so maybe Piston Miner, maybe you'll finish implementing it before I do. Especially because I only implement it in like 3-hour spurts at a time. So if I do IL basic block dominators, if I do current MLIL dot basic blocks 0, because I'm wanting the first one. I just pointed at my screen and y'all can't see that at all. So I want this this one here, and I want the reaching condition for this one here. And so first we can do that and say, okay, yes, this one can be reached by that. It's dominated by this block, which means that this block should come before it in the sequence. And then we can just do current medium level IL. I know, right? I try to show off your features, Peter. Then we can take the branch dependence, and we see that is actually the reaching condition of this basic block, because the conditions really are if EAX doesn't equal 1 or EAX doesn't equal 1 and it doesn't equal 2 and it doesn't equal 0. So or it doesn't do this, or it doesn't do this, then it comes down here. And so basically, like, this doesn't matter, because it's gonna, no matter what, it's gonna go this way or it's gonna go this way, and at that point it doesn't matter what EAX is. So yeah, from this block, I think, because this one would be where it goes otherwise. But this is basically like the else, or like what comes after the else statements. So yeah, I think I think all I need is branch dependence. That's the way it looks to me right now. And I think because of the fact that this, so if we ordered these, like the sequence and stuff, all of this stuff, it would be a sequence of this basic block. Actually, let's unhighlight. Can I do highlight instruction? Yeah. I wish there was I should have set up a key binding. Y'all need to get the key binding thing in here so I can dynamically set stuff. So our top sequence, no, I hit the wrong one. Our first sequence is going to be these. And then underneath that is going to be, or in the sequence is also going to be a condition block. And that condition block is going to have all of these. Whoop, wrong one. And I'm not going to care like what order these need to be in as well. I'm just talking about this right here. And then this is going to also be in the sequence, I believe, and come before this. But this is, actually, no, this is going to be a condition as well because it's the false branch. So what it would end up starting out as, if we go back to the paper, they talk about it down here. They start out like this, where they just do like if condition, then this block. If not this condition, then this block. So starting out, the first thing that it would be is it would be these in the sequence, then a condition block in the sequence with a if EAX doesn't equal 1, and then all of this stuff would be contained in that condition node. And then there would be a second condition node that is going to be if X equals 1, it'll do this. And then finally will be this block in our sequence. Maybe that makes sense to everybody. And that's what we're going for. So yeah. But I think that kind of shows that branch dependence is really all we need. Well, whether or not it's dominated by a basic block, and then it's branch dependence. So if we go like here, if we look at this one, current MLIL 96.branch dependence, you see tad fuzzy on their root algorithm. When they say structure a region, do they mean collapse the nodes headed by the region into an abstract node? Because if the region has a shared successor, you can't collapse that into the abstract AST unless you do their single successor transforming thingy, which I don't think they do at that point. So I think that they collapse region nodes as far as possible, and if they do have shared successors, it's still a tree, I think, isn't it? No, I guess it's just a graph, directed graph at that point. Huh. I'm not sure yet. So let's see. It has a shared successor. Well, I don't think actually you have shared successors because, like, it doesn't point into the middle. Okay, so I don't think that's the case here. because what they do, I think, is they end up ordering the blocks. And so, like, in this case, You would structure the bottom of, yeah, so you start with this node, then, actually, no, you start here. Can I clear all of these easily? Is there any clear highlight? No. There is no clear highlighting. I need that, Peter. Give me a clear all highlighting. Because how do you do? Anyway, you pick one of the deepest nodes from. No, I don't think you pick the you don't pick one of the deepest nodes. I think you pick the deepest node. So you pick this one. So you would grab this node, and this is a sequence. Then, like as an abstract node. Then you come here. No, not that one. 96. So then you would come here, and now you've got another sequence, and I think these are two disjoint sequences now. But there is no multiple deepest ones. They're always guaranteed to have some sort of order because of the depth first search. So whatever the last thing you found in your depth first search is going to be your deepest node. So like here, it looks like you have two deepest nodes, but you don't, because this one, if we start at 104, and this one is 195, so we would go to this one next. It's not, but it's not the order, depending on your order of iteration. You're doing post-order iteration, which is determined by your depth first search. And I guess, yes, you could say, like, if you chose to go all false branches first, and then all true branches, but that's which node you pick out of n successors is not set. I think it's pretty well formed, especially for our case here with medium level IL. The order is always going to be set. So depth first search means always taking true branches first here. That's how they determine the numbering. So if you see here, 6 is here because it's down a true branch. 10 is here. Oh, then it takes the false branch. Then it comes back over here and it takes the true branch. So that's not depth first, actually. I'm actually really confused. It used to be that this would be 10, or this would be 7. I am super confused right now. Huh. Yeah, I don't think it matters too much. You're still guaranteed that, like, because of the way the depth, you're guaranteed that there'll be the successors will always be checked before the predecessors. Yeah. So anyways, and now I can't remember what I was going to do. So yeah, we're going to start here. We make a sequence node. We make a sequence node here. And then we make a sequence node here. Starting here. And then here we make a condition. And we're going to bring this sequence node into this condition node is going to contain this sequence node as a child, or like as its root of its stuff. So then we've got a sequence node and a condition node, and then this is going to be, I think, the true goes here. No, actually, this is going to be under the sequence, I think. Let's go look this up, because that is an interesting thing, because we're going to look at the reaching condition for this, I think. And do we need to match the condition to it? Because the reaching condition is going to be this block, and it's going to be not this condition, and or true condition and false of this. So maybe we do need this reaching condition thing here. Man, decompilers are confusing. I've only like half read this paper, so we're gonna see how far we get with only like half reading it and kind of just kind of figure this out. Seriously. Yeah, so it looks like they tag their sequence nodes first. Also, I noticed that they have these they reorder them in a single sequence node, then they have the conditions. So I don't really even know if so they say like the initial AST, but like, I don't know. It seems like maybe those are considered condition nodes, these right here. And then this is maybe a sequence node or a condition node where, like, if true. It seems a little... Finally, a condition node is made for in4. Okay, so these are the condition nodes. So yeah, so here they just are just like, here's basic blocks in a linear order, and we tag them with a condition. So I guess let's try to do that. So we've got our reaching condition, and then we structure the acyclic regions. So we're only going to do acyclic regions right now. We've got the reaching conditions from the region header to every node in the region. And let's see, they've got a graph around here somewhere. Yeah. So they've got 3 regions. This is their head node. This is their, like the last node. So how do they determine the regions? Yeah, so that's a region. That's a region. Okay, so we perform this to find back edges to identify cyclic regions. We can do that pretty easily by just doing like E for E in current MLIL basic blocks. Let's do oh wait, no. E and BB dot outgoing edges. I think we can do something like that. Oh, did it backwards. Cool. So we've got those, and well, damn it, I accidentally locked my screen. All right, so then we can do something like back edge. No back edges, hooray! If we do something like, what is it, phase 2? Yeah. Look, there's a back edge. We can, so we know that there's a cyclic region in this one. So that means that everything else is acyclic. And I guess, oh, what am I doing? I don't even know why I have that extra desktop. I think they determine the regions based on the cycles. So effectively in this one, we have two regions. This is a region, and then this is a region right here. Although actually, I think these would be two different regions. And I guess we would also have to like make a fake node here that would have both of these come into it, and then we would just get rid of that virtual node. I think that's also something that they do. Let me see. I know, yeah, virtual sync node. I think that's what's going on here. Yeah, I think they're saying that N9 is the virtual sync node. I think that's what they're saying. Yeah, so N9 is like the end, I guess. That would be like the fake exit node, like where nothing actually happens. So we've got to do that, I guess. I don't really know how to consider that. I guess we would just pretend there's a basic block that has edges going from here and here and from here. So I guess what we would say would be if the block has no outgoing edges at all, then it has a outgoing edge to the virtual sync node. And then I guess you remove those edges, but I don't know if we actually have to do that because we've got this. And if you remove all of the virtual edges, then we've still got everything we need. So maybe we ignore that for now. So let's see. So we've got our graph slices. Actually, I'm going to rename this. Although that brings up the question. So in this case, well, no. Yeah, okay. Keep thinking about like other random stuff. And I've called this test bomb 1, but we're definitely like implementing everything. So all right. So let's see. What were we going to do? We need to calculate, we need to identify regions. Let's see. I'm going to do something like, we start with the this. If we make that the head, then I want to do something, I think, of like tracking like the head and the current and the basic block. Let's do visit. What if we let's do regions dot or no, not dot edge dot target equals a new list. And I think we want to actually, we don't want to go from the top, I don't think. I think we need to go from the bottom. So this would be a region. And then it would come in here and it would say, okay, back edge, this is a region, and it's, I think these two would be, because this is the loop. And then this would be its own region, I think. Because if we, let's look at that thing again. Because I think they had, yeah, anything that goes out is considered another like region in the loop, it looks like. Although why is this loop in this region? Shouldn't that, or is that considered part of this cycle as well? I guess because this is part of this, it's part of two node loops, that it's a single region. So I guess a region can have more than one loop, but it has at least one loop or no loops. So this would be a region. This would be a region. And then this one seems like it would have a lot of regions. It doesn't help that there's all these like no returns. I don't know why I picked this dumb thing. So I think it's something like this. Although maybe these aren't considered to be regions. But I think it's something like that, where those are the regions we would have. Well, if you go from the top, you're not visiting in post order, though. Wouldn't it be starting at the bottom and then building up the regions from there? You start at the top, okay. So we start at the top, and we have you start a post order DFS at the top? I could have sworn you started it at the bottom, because post order would be the end. I thought. Let me see. So the first thing the postfix operands has is, for this right here, is the 1C. Prefix would start at the top, which is the comp. Right, but the root is the DFS. The entry node is the root, but that's not post order then. The post order would be starting at the end of the DFS. Let's ask Wikipedia, because I'm getting confused now. Post order. Oh, okay, you are right. I am sorry. You are right. So we start here, visit there, visit there, visit there, visit there, visit there, visit there. So yeah, so we do the left. Okay, so we start here, we take the trues and come here, come this way. So I think then we order these so I guess the root node isn't considered a region. These are considered regions. If we recursively so then this would be a region. We come here, create a region here. All right. Basic block 0 is not really considered part of a region based on that that graph that they showed. So let's do let's do recursively like they say. No, let's I don't want to recurse. I want to iterate over it. And I'm going to reverse this because I want it to be like that so I can just do a pop. And no, this is going to be an edge. It looks like they identify the it said that they identify the regions with back edges. The first thing that they do starts by performing a depth first traversal over the CFG to find back edges, which identify cyclic regions. Yeah, so that's the first thing that it does. And then it tries to structure the region headed by the visited node. So we're going to find the cyclic regions first. Not regions, period, but I think you're basically, when you're identifying cyclic regions, you're breaking it up so that the acyclic regions are going to be everything in between the cyclic regions. So it looks like, for one thing, A is not in any region for some reason. So I guess the root of the CFG has no region. And so I think the first thing that you would do is say, okay, not A is a region and A is a region. And then from there, identify cycles. Like it would first start off as being, this is an entire region. And then this is a region. And then go down into these and say, okay, here's a cycle, so split these two into regions. That would be my guess. Tries to structure the region headed by the visited node. Yeah. So I think it does depth first. These are all fake nodes, I think. Aren't they? Yeah, I think you create regions and and then you use those regions later. Structuring a region is AST of control flow inside the region and then reduce it into an abstract node. So they find the regions first, then they determine what a region looks like. No, I think you have to determine the regions first, because they say right here, structuring a region is done by computing the AST of control flow inside the region and then reduce it into an abstract node. So you can have a region, and then that region might get smaller, and as you add more structure, like with the changing the things to have single successors and stuff like that. Yeah. So I think right here we would kind of go through these nodes until we find a back edge. And then that would break up this region. And then we would continue going, I think, to see if there's more, because that's the thing that gets me here. Let's see what we can do. Let's try to actually get something. We want to recursively depth. Yeah, it's pretty ambiguous in places. So we don't want to visit this right away. We want to visit this first and then visit its children. So what we're going to do here, let's get rid of this and we'll do it later. If edge, actually target equals edge dot target dot outgoing edges to visit dot append edge and to visit equals no, let's do it like that because that doesn't create a new list. Reversed target dot outgoing edges. And then if it doesn't have any outgoing edges, oh, and seam. We need to actually, no, we don't do this. Yeah, we do that, but we don't say we've seen it. I don't know. I think they do one pass. They might do multiple passes. I know that they do a couple of different. Wait a second. No, you'd visit this node last. These little dots are where they visit things. You start at the F, but you actually visit it last. Okay. So that's what I was saying. I think we were saying the same thing the whole time, but like not understanding that we were each saying the same thing and arguing about it. Or debating it. It wasn't really arguing. Okay. I think you end up seeing each of these twice unless yeah. I'm gonna do this instead. If we do it like this though, I need to say I don't want to push the next time it comes up here. So I need to be able to say, let's just do it like this then instead. Wait, no. No, they add a virtual node at the end, I think. And that's... No, I think they just say, like, what is... I think what they do is they find the cyclic nodes, and then from that you can just infer what everything else is. Like, we might not even need to do this. We might be able to just do like a loop over edges and be like, if those edges are... By the end of the DFS, you have more than one abstract node, one for every region. Yes, except they say that eventually it becomes a single abstract node. because I think once they've identified it into once you've identified all the cycles, all of the regions are going to be acyclic because all the cycles are going to be contained within a single region, or like their own regions. And so from there, I think it's almost trivial to order everything. So maybe they do it multiple times, but it's a lot easier after the first pass. All right, let's see. You get the CFG, constant propagation and dead code elimination. We don't really, we'll do that later. So how do they know? Okay, so first, so they do, I think, a depth first traversal. That gives them the back edges to identify cyclic regions. Then they visit nodes in post order. So I think they do again another depth first search. Which actually, no, that makes sense, because if they're doing the depth first search, yes, I think they can check when visiting, because when doing the depth first search, the node that has the back edge is going to be visited before the head of that region. And so I think you build up so descendants of a given node are handled before n is visited. So when at node n, our algorithm proceeds as follows. If n is the head of an acyclic region, which means that it doesn't have a back edge, then they can take the set of nodes dominated by n and structure the corresponding region as if it had a single successor. So that's when they do the virtual node or something, I think. Which is 4b, structuring acyclic regions. So at this point, they compute the reaching conditions to every node in the region. So actually, if we do this, so we already have back edges. So I don't think we have to visit these in the order that they say. I think we can just do them. We can do them in a reversed order, I think, and just start at the bottom and go from there. So we can, let's do this. So if we have cycles, is gonna be BB for, oh no, E.target if, no, for BB in basic blocks for E in BB dot outgoing edges if E dot back edge. I don't even need to. So we've got our cycles. This will give us our basic blocks that are the heads of the cyclic regions. So then we come in here and do for reversed basic blocks. Starting here, we can say if BB not in, wait, let's, cycles equals identify cycles basic blocks. If BB not in cycles, then BB must be the head of an acyclic region for the moment. So yes, for the moment. Until we get to the next thing. So we make acyclic regions and they just get bigger and bigger and bigger, I think. So, regions BB equals BB dot, let's see, dominators equals BB dot dominators. Wait, no, I want to set. So region equals BB dot dominators. Turn this into a set, and then if, let's see, how can I do, how can I most efficiently find, I guess I've just got to do a cycle or C in cycles. If C in region, then region equals region minus set C dot dominators. I think you can do that with a set. Let's make sure. I think I can do that. Yes, cool. So we remove all of the stuff that C dominates and BB dominates. And that leaves us with just the things that BB dominates that are not in a cyclic region. Actually, let's change this around. No. And I'm gonna say for region, or R in region, if R in regions, then I don't want that list there anymore. And that will remove any subregions from our list of regions. And then we should just be able to say regions BB equals region. I'm thinking though, I'm wondering, let me look at their picture of their region. I think that might be good enough. Yeah, they're supposed to have a single successor and a single predecessor, I believe. And that's where those like fake nodes come from. Let's see what happens when we do this. Let me see, where am I? Wait, no. I should really put this in the decompiler stuff. I think we're okay. All right, ln-s pwd compiler. I need to just like make an alias that does this. No, I don't want to save that. Taking a long time to load. Oh, that's because you loaded the wrong one. Okay. Loaded a test build I had accidentally. No, what are you doing? Where are you? This is the one I want. What the fuck? It updated me to the stable, maybe? Accidentally? All right, hang on a second. Let me look at some stuff. Yeah, it moved me to stable for some reason. Let me fix that. I gotta wait for it to download the thing. Also, it forgot everything about my where my window was. This will not do. Can't use stable. Oh my gosh. Are you kidding me? What the hell is going on with downloads right now? Holy shit. I have a solution for this. Yo, figure out what's yeah, we're just gonna sit here and watch it download at like 1% every minute. You really think it's gonna speed up, Jordan? I'm fixing this right now though. I have a secret weapon. What is going on with your like CDN or whatever? Like, this is ridiculous. Maybe I should switch to like Azure or something. All right. While that downloads, well, okay, you were right. It just jumped like massively, but there we go. Finally, god damn. I'm gonna have to try and cut this part out of the highlight. I think I can do that on Twitch now. There we go. Jeez. All right. There we go. 1548. Much better. And it forgot everything. Don't know why. Okay. Oh. Cool. I have Decompiler. So Decompiler import AST. All right, so what did I call stuff? Actually, you know what? Maybe this will be a little better. Actually, I want phase 2 equals bb.functions, bb.getSymbols. Is that symbol by name? No, I'll just do this. This is easier. Phase 2 address. Oh, that didn't work. Oh, right. I don't know what I'm thinking. All right, so phase 2, from decompiler import ast, ast.calc, wait, not reaching condition. Wait, identify regions, phase 2.basicBlocks. See what happens. Oh, I didn't return anything. Haha. All right. Let's do that all over again. Actually, you know what? Even better. Oops. Got a lot of stuff. Where's Memilio? Shit. I don't remember. Oh, it's an effing round. That's right. Really? Why do you open it in that one? It just opened it in a random Google profile on my other screen instead of in the one that's directly behind it. I need a token? Why is a token on? It was 8,000, right? No, 888. There we go. Okay. Let's go ahead and just make a new Python notebook and Ninja import. This will be easier because now I don't have to retype all this stuff and I can just keep running it. And then phase 2 equals bb.getFunction at bb.symbols, phase 2 address. Cool. Okay, so then regions, oops, from decompiler import ast. Regions equals ast.identify. All right, I don't have. Regions equal ast.identify regions. And then we'll do phase 2.basicBlocks. And then let's see what regions gives us. I think this is about right. So this one has 2. But this is also, it's also here. Wait, no. No, it's not. Ah, it didn't remove this block. Didn't remove this, so... Wait, no, it did. God damn, the ending of the basic block being the same address as the start of the next basic block is really confusing. Always gets me. So I think this is correct. So if we, let me see, can I make this, how do I, can't remember my, can't remember my spectacle commands. Let me see, I want this in the upper left. There we go. And then this one I want in the bottom left. So if we go to phase 2, so 8048B8E is this one. And that one thinks that it has, no, that's not it. God damn. Wait. Why does it think that it's that this one is in that region? That doesn't make any sense. Wait. Did I mess up my sets? No, that's what I want. How the hell did this get in there? This one should only be this, because this doesn't dominate this. Or did I get that backwards? Did I put the things that dominate? Yes, I did. I needed the reverse dominators, which fortunately I calculated somewhere. Oh no, did I get rid of it? Shit. Because I thought I didn't need it, and I do. All right. Actually, I just need a set. Doesn't really matter, but yeah, I'll just do a list. It's probably faster. Actually, no, it is better if I do a set here, because then I can just get that set. Oops. Oops. Let's try that. That looks a little bit better. Let's see if that makes any sense. Yeah, so that is slightly off. We want to not do the main basic block. Actually, we can just do this. Oops. Oh, it's a reverse iterator. Whoops. All right, fine. So then if yeah. So I need to do let's see if what do I want to do here? So if we So if I start here, wait, I need to actually, not even the right thing. Not that it matters too much. So actually, now that I'm thinking about it, I think that these are both technically in the region with the cycle here. Because I think the back edge is where the cycle is supposed to end, but we need to like the block that exits the, if there's more than one exit block, then they create a virtual node that is that like in the next region. So I think that actually these are all in the same region, because if we go back and look at that, if we look at this here, these two both are exit where's D3? Yeah. I guess these are just considered nodes that have conditions that like are branching. And these are the unconditional ones. Man, this paper is like super disorganized, if you ask me. Let's see. All right. Computing the AST of control flow inside the region and then reduce it into an abstract node. Almost is like recursive. Tries to structure the region headed by the visited node. So I think I create a region at the visited node. transform it into a semantically equivalent graph. But then they say the last iteration does it. It almost sounds like it's only the cycles that really matter whether or not they have various exits. Which the loop is entered. Yes, so the exit stuff is only for the cyclic regions. So I think that once we know where the cyclic region is, that's the cyclic region is a region, and then anything that's not in a cyclic region is another region. So I think elif bb in cycles, then and here anything that's dominated by it is now how do we figure out the exits? What was that picture again? So yeah, I think we're just gonna not deal with cycles just yet. Let's see what happens with That didn't work. Oh wait, maybe it did. Maybe phase 1 is really small. Yes, okay. Oops. Let's do phase 3 instead. There we go. Phase 3 might not have been the one I wanted to do either, because that's the jump. But I think this is correct, because this is all an acyclic region. So it gave me 2 regions, which is going to be this one over here, and then all of this here. What about main? Let's just do this. That's easier. Nope. Oh. Duh. All right, looks like I get 3 regions there. I think my mistake was trying to, so 1 region here. 2, which is that region. And then one. Where are you? A30. A30. Okay, so it is its own region. Interesting. How did that work? Is it because none of those are its dominators? Ah, yes. Because it's not its dominators, yeah. That actually worked. Because these don't dominate that one, so it's outside, so it's its own region. So then we order the regions. Seems like it works to me. It's just the cycle thing is the identification of where the cycle actually ends. Which maybe I need like something a little bit more complicated that that has like a cycle in the middle of the regions. Because I wonder, like, their graph doesn't really show it. Maybe like, maybe you just subtract the stuff that's dominated by maybe I need the back edges as well. Yeah. I think for E in next E for E in R dot outgoing edges if E dot back edge none. Then region equals region minus dominated R. And so then that'll give us just the things that are in the cycle. I think that's what we need. And if R in regions, and I think and BB, wait, no. We'll do this again up here. I really should just do another list, because here a back edge node isn't going to be the root of a region. Let's see how that works. Maybe I have some, yeah. Oh, whoops. No, that didn't work. Everything is just a region of itself. Let's see, which one of those is... Oh, you're not even here. Yeah, that would be a problem. Did I forget to add to the region? I did. That'll do it. Aha, look at that. I think that is correct. Oh, damn it. Y'all need to add those. Oh wait, I know what I can do. I think I have to do this. Yeah. That just gave me the keys. All right, so 6E. 6E is its own self, which is correct. 6-9 is also itself. 7-6 is this one and that one, which is correct. And then 8-8 should not be here. Wait. What the fuck? Oh no, that's right. That's not what I want. I don't want to just do this. I want to do all of this with, and then re-add R back, because R needs to still be in it. And I think this one still would be part of the region. Because it's an abnormal exit. So these two are it's got two exits, and then this is not considered part of it. At the very least, if it's not working, yeah, so we have those three, and then each of those is its own thing. I think we have identified our regions. And then this one is ridiculously long because it's an acyclic region of a switch statement. And then main looks correct. Let me look. What's 4 look like? That's going to be 2 regions. Ah, this one's a good one. It's got a loop in the center. So let's see what that one looks like. That works. Right. (6b) is a region. With 6b, this one and that one. Okay. 5-7 is a region all by itself. That's correct. 4-8 is a region all by itself. Correct. 4D is a region all by itself. Correct. I think that actually works. I mean, I might have some corner cases later, but it seems like those are the regions without doing their optimizations. Or like their cleanup stuff to do stuff. So that's pretty cool. Now what's the next part? I don't really want to deal with cycles right now. I just want to do one of the other ones. So I think then they use these structuring acyclic regions. We can order its nodes linearly such that for any directed edge UV, U comes before V in the ordering. They compute the reaching conditions from the region header H to every node in the region. Next, we construct the initial AST as sequence of code nodes in topological order associated with corresponding reaching conditions. Represents control inside the region as if reaching condition, then node. If reaching condition, then node. Okay, we can do that. Okay. I probably can put these in the AST. We'll do that later. I want to do so let's go ahead and say structure acyclic region. All right, so they call it a header, right? Yeah, region header. All right. Reaching nodes. Did I put that under the wrong thing? God damn it, I keep doing that. Maybe I should move some of these to a different file. So let's go ahead and move this into here. We don't need to return anything here now. We can just say self.reaching conditions equals reaching conditions. All right. So here we can do for BB in region. If BB is the region header, I think we just don't do anything. So let's see. Ordered region is going to be sorted let's see. Oh, I can't do a sorted key there. Key equals none. Used to extract a comparison, but I don't get both. All right. Damn, I wanted to just be like, sort them. Is there a way that I could say that? I don't want to write a sort order. Is there a Python quick sort? I need a sort that takes a comparison function. No, I don't want to. Python sort function with comp. Damn it, that doesn't help me at all. Because I want to be able to say if item 1 is dominated by item 2. Comp to key. Let me see, func tools, comp to key. That is what I want. I don't know how you would convert that, but they apparently know how. would be sorted region key equals comp to key lambda I j I I1 if I in j dot dominators else 1 if j in I dot dominators else 0. Let's try this. Ugh, I messed it up. Oops. All right. So if we do a dot calculate reaching conditions. Well, oh, right, because I changed my thing. Hang on just a second, let me fix this. All right, let's fix this real quick. I need to get that. Need to finish that that hash pull request. Gotta go and change the things. Okay, cool. All right, so should be able to do a reaching conditions now. Yeah, cool. All right, don't need those, but we want to do regions equals identify. Wait, no, calculate. Oh, no, AST, identify regions. AST dot Does function? Does it have a function? No. Actually, what's ast.children? No, that's not it. Okay, regions equals ast.identify regions, and we'll do main regions because I believe that's up there. Nope. What the hell? Isn't that there? Yeah, get dominated's there. Oh, key error. Huh? Dominated should have... everything? How is that possible? I literally set it up right there. You can't have a dominator that's not in... What the... Let's try that again. The hell? Oh, it's because they're not medium level, I think. Wait, no, that doesn't make any sense. Oh, I did mean regions. Yeah, there we go. That was dumb of me. I should probably be checking the types of things. All right, so we have our regions. Yeah, that looks right. Okay. And structure acyclic region. Let's do the one I want. Oops. All right, let's see what kind of ordering that gave us. So that would be this one, then this one, then this one, then this one. That's not bad. I mean, that makes sense. I can do either of these in any order and then do this one. And so then we would do the reaching condition for each of those. Go ahead and put this in here too. I should fix this one too. All right. So here, I feel like that worked pretty well. I'm surprised I got the -1 and the 1 correct on the first try. I really expected that to be the wrong order. That had the yeah, that had 6 in it. Cool. All right. So we'll take this out. I want to add let's do region nodes equals actually let's come here and in the sequence I feel like I want to make these basic blocks. No, I know. What do I want to do here? Isn't there an instruction node? Why do I not have an instruction node? Oh, because I haven't defined it yet. Wait, annotations will handle that. I don't know if I like that. I keep going back and forth about doing these as instructions or not. Maybe I should do them as basic blocks. Yeah. I'll just deal with when I'm outputting, I'll figure out the last instruction. All right. I'll just make a basic block instruction. All right. And I want this to be an instruction. And this makes sense. And we'll deal with these later. Okay. So if the region header can do it like that, and region nodes, region node equals EMLILAST sequence node with ordered region. Oh wait, no, region headers. Oh, and my AST, because I'm still passing that for some strange reason. I think I can actually just do region node dot, oh no, So here is where I need to convert the I can't make this an IL instruction. I'm gonna have to make another. I'm just gonna have to pull that out for now and pull this out. It's gonna be a list. But what I need to do is make a new thing, medium level ILAST condition this will be the I wonder if I can generate this. No, I don't think I can without making a I wonder if I can make a medium level IL function. I don't know if I can do that without it actually having a function tied to it. I know you can do it with low level IL. Because you can do it with a low level IL function. Oops. Oopsie. But you can't do it with a medium level. Although, I can... Is there something I'm missing? Ah, that's what it is. Oh, no. Can I do... Oh, they don't have all of them set out. That's okay. I can make it. Well, there's some of them. Where? I guess not all of them are made. This is gonna be complicated. Let's just do... Actually, no, let's just do... Nope, wrong type. What did I? Oh. What did I mess up? I know I'm not supposed to be doing this, so don't yell at me. Type error is wrong type. All right, let's just figure out what's going on. All right. Is there not a... They're not a knot? Is that what I'm messing up? No, there's a knot. Oops. All right, fine. I'll come here and look at what's going on here. All right. If is instance operation is a string. It's not a string though. What the hell? That doesn't make any sense. No? Is there something? Operation is first. All right, fine. We'll do this. Let's see now. Yeah, let's just make this one too. Now it didn't print it in a different place. 1, 2, 3, 4. Wrong type. What should A be? Is it the expression? There we go. Okay, it was just the index. Cool. So, can I do? Why did it give me a 9? It won't give it to me, will it? Actually, it gave me something really weird. Oh, it's because I need to change some stuff on that. So this is really bad things that you should not be doing, but I'm going to do them anyways. So I'm actually appending to the end of a medium level IL function that is already finalized, so it won't do anything to the basic blocks, but it allows me to generate medium level IL expressions that are able to be used as the instruction objects that I want to use to represent conditions. Whoop, just locked my screen again. Although, let's see what happens when you do this. Oh, that's beautiful. So it doesn't even affect like the instructions thing, but it's still there. Now what happens if I leave and come back? Still there, but it's not accessible through any of the other functions. I can only get to it by its index in the thing. But this allows me to reference variables and things like that that are part of this MLIL function without having to like recreate the stuff. So the thing that I can do is I can say come here, and we've got this condition here. If I want to negate that, I can do current MLIL.append current MLIL.expression medium level IL operation MLIL not, and then I can do current MLIL 5.condition.expression index. And I think that, okay. Can't see my 105. So now current MLIL 105. Ta-da! And now I can take those and I can generate from the reaching conditions. I can say, take those conditions, knot them the way I need to, and I can do something like, say, this one here would be like the reaching condition for this basic block right here would be here, let me see if I can get this to give me some more space. Yeah. Okay, and then I think, oops, I messed it up. Okay. Let's figure out, okay. Oh, and then maybe I need to make the let me make this one first, I think. No, I shouldn't have to. Oh, I did it again. Oops. Oh, yeah, that's right. That's pretty funny that I accidentally did that. All right, there we go. So you can do stuff like if not EAX not equal 2 and EAX not equal 1. So the point of this is that I want to be able to generate these instructions, and then I can later simplify them and turn them into the conditions for these blocks. But I want to be able to represent them like this for now. So that's fun. And I think we have to call it there with that little bit of a treat right at the end for something ridiculously disgusting and hacky. And I hope that y'all are still watching Vector 35 People and that you hate me. Yeah, so next time, I think that we will take the conditions and we'll be adding those into the thing. So I don't actually need this now. I can create my conditions the way I want them. And here we can do a medium level IL instruction still. So we'll add those conditions to our condition node, and then each of these will be we'll do region node dot append, and then we'll do new medium level IL AST condition nodes with our condition for this one. Yeah, so it's going to look like that. And so we'll just go ahead and say generate MLIL reaching condition. Actually, let's switch that. Generate reach condition MLIL. And from here, we'll be able to create those acyclic regions, and then we can move on to the loop and the switch. Well, actually, I think next we'll do switch, and then we'll deal with the loop stuff. I think that'll be pretty exciting. And then at that point, we should be able to start outputting the instructions again and see if we get some nice, pretty pseudocode. So until then, thanks for watching. I had a pretty good time tonight, and it was confusing as hell for a while, but I think we made some really good progress on this. I'm super excited. So y'all have a good night, and I will hopefully see you again on Tuesday at 3 p.m. Pacific, 6 p.m. Eastern. Have a good night.